Hi, I'm Chris, and in this video we're going to take a look at Hardy-Weinberg equations and how we can apply those to a typical word problem that we would see in a biology course or maybe on the biological sciences portion of a standardized test like the MCAT. So here we go. It says if 16% of a population physically display a recessive trait, then what percent of that population is heterozygous for that trait? Okay, so there are a few vocab words in here which we'll discuss as we go through. We see things like recessive and heterozygous. But first we want to take a look and see what kind of equation we should use for a problem like this, because we can see we've got some numerical values in there and they're asking us for a numerical value. They want us to come up with the actual percentage of that population that is heterozygous for this trait. So for Hardy-Weinberg equations, we know that P plus Q equals 1 according to Hardy-Weinberg, and what this means is that the frequency of each of your alleles, your dominant allele and your recessive allele, P and Q respectively, will together add up to 1, because those are the only two types of allele, which is basically a marker of what kind of inheritance you're going to have depending on the frequency of dominant versus recessive alleles. And in genetics, what this refers to is the idea that if you have a particular trait that is inherited dominantly, then that pattern of inheritance, the way that that gets passed down from generation to generation, happens a little bit differently than if something is recessive. So each gene that we have, for it to be expressed, and each trait that we have for it to be expressed, is going to have two alleles that code for that. There's a dominant and recessive allele, and we have to look at what combinations, whether you get one dominant, one recessive, both recessive, etc. So the second Hardy-Weinberg equation that we have is if you were to take this expression, P plus Q, and square it, it's still going to be equal to 1. But if we think back on maybe some of our older math, when we see something like this, it means we have to FOIL. And if we FOILed this expression and wrote it out, we would come up with P squared plus 2PQ plus Q squared equals 1. Now for this particular equation, the P squared basically represents the percentage of the population that receives 2 of the P alleles or 2 of the dominant alleles. So this is something that we would refer to as homozygous, which means that you're only getting one type of allele. And in this case, P squared would represent something that is homozygous dominant. Q squared, along the same line of thinking, represents something that is homozygous recessive, which means that you're getting 2 copies of the recessive allele. And then 2PQ, that's what they're asking for in this question. That represents the percentage of your population that is heterozygous, which basically means that they're getting 1 of each. This part of the population is getting 1 dominant allele and 1 recessive allele. So now let's take a look at how we can incorporate the numbers into an equation like this. If 16% of the population physically displays the recessive trait, well, the only way in biology that you can physically display something that's recessive is if it's your homozygous recessive portion of the population. If you have, in fact, 2 of those recessive traits. Because if you have even 1 dominant allele and 1 recessive allele, you'll display the dominant phenotype, which basically means the physical manifestation of those alleles. So here, for Q squared in this problem represents 16%. And the way that we do our calculations, we would have Q squared equals 0.16. And when we take the square root of each side, Q will equal 0.4. And if you need to double check that, you can always write out the math on that and multiply 0.4 times 0.4 just to prove that it does come out, in fact, to be 0.16. So if Q is 0.4, now we can use this first Hardy-Weinberg equation, P plus Q must equal 1. So if Q is 0.4, when we plug that in, we get P equals 0.6 from this equation over here. Once we know Q, we plug it in, and that gives us P equals 0.6. And then to find the heterozygous part of the population, which is the key that we're looking for in this question, remember, this is where our answer is going to be. This tells us what percentage is heterozygous. So here, we just plug in 2PQ equals 2 times 0.6 times 0.4, and that comes out to be 0.48 when we do the math on that, which is equal to 48%. So I'll cover a few more examples in some of our other videos of very similar problems just to make sure we get a handle on the math, because I know the math here is complex. But the most important thing to understand about Hardy-Weinberg equations is that the p squared portion of this equation represents your homozygous dominant percent of population. Q squared represents your homozygous recessive portion of the population. And 2pq represents your heterozygous percent of population, which in this case comes out to be 48%. And when you add up all those values together, it will equal 1. So as long as you know even one of these parts, you can find P and Q, and you can solve for any of the corresponding parts that a question might ask for. Please watch our other videos if you want a little bit more practice, or you can visit our website at sandersontestprep.com and check out STP TV for videos covering other biology topics and other academic subject areas. Thanks for watching.